Thank you, Rafi. Thank you, everyone. I like to start this talk by thanking, first of all, the organizers of this workshop for the kind invitation, which I've really appreciated. Of course, it would have been better to be in Los Angeles, but we will have other opportunities. I'm sure about that. Well, I want also to show you the sources that I've used to prepare this talk, which are those listed in this, or well, appearing in this slide, and also give credits to my co-authors and collaborators. You see there is Cecilia Pasquale, Silvia Siri, Simona Saccone, Carlos Canudas de Witt, Giulia Piacentini, Paola Goatin, Kalle Johansson, and Mladen Cicic. Well, the majority of the contents of the talk is included in the papers and in the textbooks that you see in this slide. Well, let's start with a few words of motivation. Well, it's pretty clear to everyone that the efficient management of road traffic networks is a crucial issue in all the developed countries. And this is particularly true since in the last decades we have observed a significant growth in the number of vehicles. And well, this growth has a significant impact on the climate, on the environment, and on our quality of life. You can see a picture in the slide. This is a picture taken by my daughter, September 2019. She was going to the University in Milano, and this is the typical situation that she experienced any single week, day. And well, something should be done. Well, apart from the consideration that I mentioned, we have also to observe that direct road fatalities are strictly related to intense and not well-regulated vehicular traffic. But just to give you an example, in the European Union, we have some of the safest roads in the world. And in spite of that, any single year, we have more than 20,000 people losing their lives on the European Union roads. And well, let me say that apart from direct fatalities, we cannot neglect the huge number of indirect fatalities. Those due to air pollution, the so-called silent killer, according to the definition of the World Health Organization, as you see in the slide. Well, if we look at the number of deaths which can be attributed to air pollution, it is immediate to notice that the transportation systems in the ranking of the causes for these deaths these systems are the second in the ranking for responsibility. And let me say that I'm a control engineer. And so in my position, it's quite natural to me to ask myself a question: what can control experts do? Which is the contribution that people like me, people like us, people having an expertise in systems and even in control, which is the contribution that we can do, we can give to this situation, to alleviate the problems, the issues that I've just mentioned. Well, we have to consider that nowadays we have new sensors, new actuators, new communication technologies, and we are able to couple them with efficient control strategies. And this can really make a difference in the systems that we are considering, traffic system. So controlling road traffic, we can make the system more coordinated, more sustainable. We can make the system safer, or in other time, we can make traffic systems smarter, so they can become smart traffic systems. This is the objective that we want to attain. And well, as I said, I'm a control expert, so I want to give you some elements of control theory to clarify the context in which I placed my presentation. Well, a road traffic system is a dynamical system. It is typically complex, large scale. It can be hybrid, it can be switched. It is definitely non-linear. It can be constrained. It is a complex system, first of all. But in spite of the complexity of this class of systems, it is possible to influence the traffic state evolution by suitably designing some system inputs. And this can be done in order to attain some these are the equilibria. And these equilibria are, of course, equilibria in which the mentioned critical issues about traffic system are solved or are at least attenuated. So this is the idea underlying my talk. Well, when we talk about traffic control, we have to consider the control objectives. There are many. If you look at the literature, you can find several control objectives. I just summarize the major ones. First of all, the minimization of the total time spent by the vehicles in the system, which means also the time spent queuing on the on-ramps, for instance, of a non-urban traffic system. Then we may have the maximization of the total traveled distance by the vehicles in the system, or we may have other kind of control objectives in which we have some set point tracking objectives to attain. And this can be done in order, for instance, to maximize the capacity of exploitation of the system, or to penalize some situation in which the traffic density or the queue length on the on-ramps exceeds some given thresholds. When I talk about on-ramps, I consider in particular some kind of extra urban or freeway traffic systems. But some similar objectives can be defined also for urban traffic. And then, of course, you may also consider other kind of objectives like safety, emission, noise reduction, energy efficiency, environmental risk mitigation. This is extremely important nowadays, and eco-driving. All kind of objectives which are majorly related to sustainability. This is an important term in traffic control. Well, I thought that it was also interesting for those of you who are not very familiar with traffic control to have an idea of the volume of research in road traffic control. And in order to do that, I just had a look at Scopus data, and just selecting as a year range, the one that you see in the slide from 1980 to 2019, and using as a keyword road traffic control, you see that I found around 16,000 documents. And well, I've just collected the data and produced some graphics for you, some plots. And you see that if you look at the plot of document versus time, you see that there is a significant increase in the interest towards these specific topics, road traffic control in the last years, in the last 2 decades in particular. And this is true not only for engineering, which is, let's say, in some sense, the traditional area in which traffic control is pursued, but if you look at the pie chart that I've reconstructed using the Scopus data that I've collected, you see that also computer science is very interested, social sciences, mathematics, environmental science, and physics, and medicine, and others. So the interest is actually wide and spread over different areas. Well, this was the preamble. Now I enter into the more technical part of the presentation, even if I wanted to remain a bit, let's say, not very, very detailed in this second part. I will come back. I will move to the details in the last part. Well, this is the outline of my presentation. Of course, my objective is to tell you something about the innovative modeling and control methods to tackle with the traffic system when we have connected and autonomous vehicles included in the overall traffic. But in order to do that, I need to start from a brief review of classical methods. And then I will reach the new methods. I will tell you something about the new methods, and I will focus in particular to some traffic models incorporating connected and automated vehicles that we have proposed and used. In particular, we have used to propose and define some innovative control approaches. Well, this is the plan. Now let's go through it quickly. Well, I start from the classic method as promised. And well, as it is natural, when you have to design a controller, this is also for any field of control theory and application of control results. When you have to design a controller, you need to formulate a model, a mathematical model of the process to control. In case of traffic control, you can have different models for different scales. This is the classical, let's say, setting. If you look if you have a look at the tree that I've reported, sort of tree that I've reported in the slide, you see that in case of traffic flow models, we can have, as I said, a model for a different scale. So microscopic models, mesoscopic model, macroscopic model. And then for any branch of the upper part of this tree, you can consider to have both the continuous and the discrete version. And again, for any branch, you may have the first order and the second order model version. And then again, for any branch, you may have a single class models or a multi-class model. This is more or less the structure. And well, in this talk, I focus, at least in this part of the talk, I focus on macroscopic model because they are majorly used, are those at least, majorly used for traffic control design in the classical approaches. Well, I start from a very, very basic and very important model, the so-called Lighthill, Widham and Richards model. Well, it was introduced in the 50s of the last century, and well, it's a macroscopic model based on the equation that you see in the slide, a PD, which is the equation of a vehicle's conservation. This model is also characterized by the fact of relying on a very famous, let me say, very well-known diagram, which is the so-called traffic fundamental diagram. A diagram which describes the theoretical relationship that you have between flow and density in a traffic system in steady-state conditions. Well, this model was the basis to develop many other models. One of this model is the so-called cell transmission model. The cell transmission model was introduced in the 90s of last century by D'Aganzo. It's a very well-known model and widely used, let me say, especially to design control systems for traffic systems. Well, this model is a sort of discretized version in time and space of the LWR model that we have seen in the previous slide. And it's characterized by the fact that the traffic stretch, so to pick a piece of the road in which you have some traffic dynamics to characterize, well, the stretch of road is subdivided into cells. And for any cell, you may write a single equation, first order equation, describing the dynamics of the density. In the slide, it is indicated with the letter rho. Rho of I means the density in cell I. And well, if you look at the picture that you see in the upper part of the slide on the right, you see that from one cell to the other, there is a flow transfer. This flow is defined using a classical supply-demand mechanism, which is depicted in the lower part of the slide on the right. So you see that you have to compute the minimum between the demand of traffic asking to enter cell number I and the capability, let me call it like that, of the cell number I to accommodate that amount of flow. Well, this is the idea of the cell transmission model. This model was originally proposed for a single road stretch, but still in the 90s, D'Aganzo again proposed a modification, introducing some new types of cells, the merge and diverge cells, which were able to describe those phenomena of, merging of two or more flows and diverging of different flow branches. And well, with the use of these new cells, it was possible to use the CTM, the cell transmission model, not only to describe a single road stretch, but to describe even a very large and complex traffic network. And well, this was an important step to remember in the history, let me say, of the research on traffic control and traffic modeling. Well, there is a typical concern which is raised when you use the CTM to model traffic systems, and especially when you want to use the CTM to design the controller for a traffic system. And this concern is related to a phenomenon which is called capacity drop. The problem is the following: when you have a physical bottleneck, think of a car accident, think of a restriction of the capacity of the road, use some work in progress for instance, what happens is that the discharge flow from the bottleneck is lower than the actual capacity of the bottleneck, or lower of the actual capacity of the piece of road which is immediately after the bottleneck, downstream the bottleneck. And well, if you look at physical systems, so physical traffic system, it can be seen that more or less this reduction is between the 5 and the 20% with respect to the ideal or nominal capacity. Well, the CTM is not able to capture this phenomenon. This is correct in the sense that you would need an equation describing the dynamics of the velocity of the flow to be able to describe in a correct way the capacity drop. So what was needed and was proposed in the literature was a modification of the CTM to account for the capacity drop. We also proposed something, and you see a brief sketch of what we presented in the paper that you see indicated in the lower part of the slide, together with Ioannis Papamikael and Marcos Papageorgiou, a very well-known people in the area of traffic control. Well, we are going to use this model in a few moments, and I go on without adding too much details now. Well, another model that I like to mention is a model which is called variable length cell transmission model, because it's a model that I've co-authored together with Carlos Canudas de Witt. This is a nice model for control. So it's a nice control-oriented model, because it's based only on free state variables, as you may notice from the equations appearing in the slide. Well, here we have the equation describing the density of the portion of traffic which is congested, the dynamics, the equation describing the dynamics of the density of the free portion of the traffic, and then we have a dynamics of this shock wave front, let me call it like that. And well, this is a simpler model, simpler than the classical continuous macroscopic model, and even simpler of the CTM, because to describe the same stretch of roads, in the CTM, with the same accuracy, you would need definitely a high number of cells. So definitely more state variables. Don't forget that for any cell in the CTM, you have a state variable. So if you have 100 cells, you have 100 state variables. Here you have 3 cells, provided that you have a single shock wave in that portion of the road. Well, in spite of the simplicity, this model has the capability of describing the relevant phenomena in traffic. And in particular, I described shock waves, he described rarefaction waves, which is, let me say, nice. And well, of course, there are other models, classical models. I've just reported some in this slide for your convenience. I mentioned the asymmetric cell transmission model introduced by Gomez and Horowitz. There are different versions of the CTM meant to encompass different classes of vehicles. I've just reported a reference, but you may find many others in the literature. And then there is the MetaNet. The MetaNet is an important model because it's a second order model capable of explicitly describing the dynamics of the traffic velocity. So this is something which may be important for control. And now, let's have a very quick look to classical control techniques or strategies. I focus the attention on freeway traffic control because, as I said to you before, I devoted the majority of my research activity on traffic control to freeway traffic control. But many ideas that are investigated in freeway traffic control can be extended to urban traffic. Well, in this case, we have 2 different classes of strategies. We have the local control strategies and the coordinated control strategies. If you look at the local control strategies, you see that to implement them, you needed to work at a very low level, performing the so-called ramp metering, this is a possibility, or mainstream control, which is typically implemented using variable speed limits. You may apply instead route guidance, so differentiating or guiding the different classes of vehicles, or maybe different portion of the traffic in different directions, and then may have some kind of integrated strategies. In case of coordinated control, what happens is that to find a solution, the control solution to the control problem, you have to solve an optimal control problem. This is the classical approach. Very often, it's advisable to include some prediction capability in the controller, and this is normally done by using an approach which is probably very well known also, to people not working in traffic control, which is a model predictive control, a kind of technique which allows to have some prediction on future evolutions of the relevant signals in the process under control. Well, again, when you go at low level, you can use ramp metering, mainstream control, route guidance, and integrated control to implement the strategy. This is the idea. And now let's move on and let's say something about the innovative methods, innovative control methods in particular. But you will see that in order to talk about the control methods, I need to introduce some models. Well, first of all, I want to mention the fact that in the last decade, we have actually had a paradigm shift. With the introduction of the notion of connected and automated vehicles, we have understood that we have really many more possibilities to control traffic in a very efficient way. Let me say more efficient than we did in the past, at least in principle. Then move to the real implementation is maybe sometimes a difficult matter, but in principle, we have a lot of there is a lot of potentialities in this sense. Well, given a traffic system with mixed traffic, and when I say mixed traffic, I mean a traffic in which conventionally driven vehicles and connected and automated or autonomous vehicles coexist, then we can control the traffic system by controlling the connected and automated vehicles. Please notice that I use the term connected and automated. I use it as a sort of synonymous of connected and autonomous vehicles. Let me say that we don't actually need a complete autonomy of the vehicles to be able to use the vehicle in this kind of a cooperative game that the traffic control at the end of the day is. But this is something that would need another lecture to be investigated in the correct with the correct level of detail. Well, let me use this term connected and automated, and you may interpret it as synonymous in this talk of connected and autonomous vehicles. Well, one possibility that we have to control traffic by controlling CAVs, let me use the acronym, is to control the class of CAVs as if it were a separate macroscopic vehicular class. So in this sense, we needed to imagine to use multi-class models. And in this sense, we can consider that we have a class which is that of the connected and automated vehicles, and another class, which is that of conventional vehicles, and they coexist. So, for instance, here you have a sort of pictorial description of a CTM model written for the two classes of vehicles that I just mentioned. This was written in this was presented in this paper. And well, when we have this situation, what happens is that starting, for instance, for a situation like the one that you see here, in which I don't have a control and you have a stretch of the road with a certain number of cells, 10 cells in this case, and you have a certain time interval, and you see that there is a propagation backwards of a shock wave. So this is a congested part of traffic, and the propagation of a congestion, what you can obtain by trying with different penetration rate of the CAVs class, I mean, with a different penetration rate of connected and automated vehicles, you can observe that we can have an impact on the overall traffic behaviors. And we can move from the no control case to a case in which you see that increasing the penetration rate, we reach a regularization of the traffic and the significant attenuation of the congestion. And well, of course, the effectiveness of the control in this case strictly depends on the penetration rate, because if we have two classes, one is controlled and the other is not controlled, the ideal case would be to have all the vehicles belonging to the controlled vehicle class. This is in some sense, the ideal situation. Well, another possibility when I have cars in the traffic is to control the cars individually. And well, in principle, it's doable. Of course, you have to consider the fact that you can move to a completely decentralized control case in which you control any single connected and automated vehicle alone, just receiving some information for the other vehicle, but neglecting what is the optimum for the overall system, or maybe consider a form of coordination. And well, the idea would be to reach a balance between a completely selfish behavior of the single vehicles and the social optimum in a sort of game which can be completely non-cooperative or maybe a bit more oriented towards a cooperation. And well, the final case, which is that of having platoons of vehicles. When we have cars immersed in the macroscopic traffic, we can consider to create a sort of a coordination of the cars in order to come up with some formations. They can be platoons or they can be even more complex formations. Well, here you see in the picture, I've just reported a case of a control of platoons via a centralized controller, but also in this case, we can think again to have some local controllers of the platoon and again, some form of supervision in order to come up with some coordination. And well, platooning, vehicle formation generation, is something which is used in this context with the aim of creating in practice an artificial moving bottleneck or more artificial moving bottlenecks. So in order to solve the possible congestion created by physical bottlenecks, we inject in the system sort of moving bottlenecks, which are used as a sort of special actuators to control the macroscopic traffic. This is the idea. I want to bring your attention to the fact that when we use the first approach that I mentioned, that of controlling the class of connected and automated vehicle as a macroscopic vehicular class, we are using a single scale modeling in the sense that in the model we have a class which is a macroscopic class of vehicles, which are the cars, another class which is a macroscopic class of vehicles, which are the conventional vehicles. When we use the other two approaches that I've just mentioned, the control of the cars individually or control of the cars in order to create platoons or other formation, we need a multiscale model. And the reason for this is that in the case in which we want to control the single car, create the formation and control then at the end of the day, the macroscopic traffic, we need a model which includes all the single scales. So we need to be able to let's say, follow the dynamics of the single car, follow the creation of the platoon, influence the creation maybe through a suitable level of the controller, and then be able to reach the objective, the control objective for the macroscopic traffic. This is the idea. And well, I want to finish my talk, dedicate the last part of the talk to show you some mixed model, multiscale model, let me say, that we have proposed and used with also an example of how to use them for traffic control. I start from an extension of the CTM that we have proposed to include platoons of cars. And well, the idea is very, very basic. Let me say, we start from a classical CTM equation. You see, this is the dynamics of the density in a cell, and we add a term to account for the presence of moving bottlenecks or platoons of cars. And well, in this part, you see this variable O with subscript J is the occupancy of the moving bottleneck number J, and this variable delta is a binary variable, which is used to indicate if a bottleneck, a platoon, enters a certain cell. The presence of the platoon in a cell goes to modify the flow speed, the so-called free flow speed. If we don't have a platoon, we have the nominal free speed. And if we have the platoon, we have a free speed, which is a function of the velocity of the platoon, here indicated with V over bar. And there are cases in which maybe the velocity of the platoon in some sense becomes dominant, and this becomes, in practice, the velocity, the free velocity of the cell. And this is the idea. We have used this model, and this model has been used in particular in connection with an MPC control approach. And we have used it in the sense that you see in the slide. So the control variable was the speed of the platoons. So any platoons, in practice, you can look at the picture, any platoon in the traffic flow is a sort of actuator, which is capable of influencing the free velocity of the traffic flow, and the control variable is exactly the velocity of the single platoon. So we have a vector of the velocities of the platoon, and the control problem was that of finding the optimal sequence of the control vector U, minimizing the cost function that you see here. So you see the first part is the total travel time that I mentioned before. And then there are two terms which are actually oriented to alleviate the capacity drop effect that I mentioned before. If you look, the second term is just a term which is placed here to maximize the discharge flow from the bottleneck. And the last term is just a density error. So we put in the cost the density error, and this is oriented to keep the density below the critical value. And this is what we have done. If you want to have a look at an example, this is a road stretch with 16 cells. This is the length of any cell. This is the time interval that we have used for simulation. We are simulating a couple of hours, if I remember, yes, a couple of hours. And we applied the MPC with 20 time steps of prediction horizon. What happens is that in the simulation is that we have created a sort of temporary physical bottleneck, like a car accident, a work in progress in a cell number 13. And this reduces the capacity from the nominal value, which is 6,000 vehicle per hour, to this other value, 5,400. And what happens is that during the simulation, we assume that several cars enter the road, and they are controlling, creating 13 platoons. And this is what happens in simulation. This is on the left. You see the case in which we don't have any control applied, and we don't have any capacity drop modeling. So we just look at what happened in open loop in a very, let's say, non-realistic case. You see that having a physical bottleneck in cell 13, we have a propagation in time of the congestion, but you don't see the creation of the shock waves, which is something which in practice actually occurs. And if we introduce the capacity drop model, the variation that I mentioned before in the model, in the CTM model, and still we don't apply any control, we see in the second picture, the one in the center, the propagation of the shock waves in the cells which are upstream with respect to cell number 13. If we apply the control, so if we control the 13 small platoons of 2 vehicles, just 2 vehicles, 2 connected and automated vehicles, you see that what happens in practice, that we go back to a situation in which the capacity drop is not effective. We don't see in practice anymore, at least not as visible as it is in the second picture, the one in the center, the effect of the capacity drop. The idea is that instead of having a major shock wave, the small platoons create some small shock waves which contribute altogether to mitigate the back propagation of the congestion. And this is the idea of how to use this approach based on curves to control the system. And the congestion is mitigated, the travel times are reduced, and this is done even with a small number of cars. That's nice. Let me say something which should be, let's say, observed and maybe exploited even in real world traffic. Well, I want to conclude the talk by presenting another model. I go very quickly on this, and this model is instead a kind of mixed model in which we have a PDE and the order, or more than one ODE, which are taken together. They are coupled. Well, we started from this model, which was actually introduced by Maria Laura Delle Monache and Paola Guattin in 2014. And we used initially this model to perform some control. I want to say a few words about the model. So you see the first equation is the classical LWR model. And then you see that we use a constraint, and this constraint is a constraint on the flow, which is in practice a constraint occurring at the position where the moving bottleneck is. In this model, we assume in practice to have a sort of point-wise in space moving bottleneck, which is a bit unrealistic, let's say, assumption. And what you see in the last part of this system, we have an ODE, which is the ODE describing the trajectory of the moving bottleneck. When we use this model, which is anyway a nice model, a multiscale model indeed, when we use this model to control the platoon of the moving bottleneck, in this case, it's a very pointwise, as I said, so it's not nice to talk about platoon. Let's call it moving bottleneck. If we use it again by using model predicted control, we can get a good result, but the result, let me say, was not completely satisfactory. I will show you the result at the end. I want to show you before how we have decided to modify the model. And well, instead of using the model that I've just shown you, the coupled PDE model, in which you had a single ODE and a single PDE, we decided to extend that model in order to be able to capture the presence of platoons of curves. And considering also that not only the velocity of the platoon varies in time, but in this situation, also the length of the platoon can vary. And well, this is obtained with a model like this, which was proposed in this paper that appeared this year. So it's very recent, written with Giulia Piacentini, my PhD student, and Paola Guattin, a very nice co-worker of mine. I like a lot to work with Paola. And well, you see, we have a macroscopic traffic flow model, which is in practice the LWR model. And then we have two ODEs describing the trajectory of the initial and final points of the platoon, so the front end and the back end. And subtracting these two equations, we can come up with the dynamics, the equation describing the length of the platoon. And this is a nice model, but there is a caveat. Well, in this model, because of the presence of the platoon, we have a discontinuous flux function. We have a discontinuous flux function because maybe it's better that I show you the next slide. But what happens is that in practice, when we have the platoon, we have a capacity reduction. And well, this is depicted even by this picture, but maybe it becomes even more visible in a second picture that I'm going to show you. Well, let me say, we have the platoon entering a cell, and the platoon has a length, so it's not pointwise. And so in any cell in which we have the front end and the back end of the platoon, we have discontinuity in the density in the cell. While in the classical, let's say, cell discretization that is used to solve the LWR model, we have that inside the cell, we have a constant value of the density, not a jump of the density. And well, the literature on conservation laws having this continuous flux function is vast, this must be said. But most of the literature focus only on discontinuities at the fixed point in space, while we have discontinuities moving together with the platoon. And this is the picture that I was mentioned before. So you see, we have the platoon. Here we have some constant flux, I mean, non-discontinuous flux. This is better to tell. It's not, it has, the flux is given by a demand supply mechanism as always, but here in the interfaces where we have the passage of the platoon, we have some discontinuous flow. And well, what we have done was just to use a sort of regularization method. So we have considered that in the cell in which we have a front end, but the same holds for the back end, we have a jump. And so we have approximated the density in the cell with the value associated with the previous cell in this side of the discontinuity front, and with the value associated with the downstream cell on the right part of the discontinuity front. And when we have this approximation, well, now the situation becomes in some sense easy to deal with, in the sense that we can solve a Riemann problem using the values of the density on the left and on the right of the discontinuity front as initial condition. We come up with a solution of the Riemann problem, and we notice that the discontinuous front, to reach the interface, needs to have some time. So it takes some time to reach the interface. And well, we need to use a numerical method to reconstruct the flux, and of course, this has helped us to deal with this non-classical shock case. And well, I'm finishing. This is what you see in the density space plot. You see here in this picture at time 0 the position of the platoon versus space, and you see that when time goes by, the platoon moves, creating some shock in front, some rarefaction wave here, another shock wave. And the same happens in the following time instant. And in particular, you see that the creation of the backward, the shock wave behind the platoon is moving towards the right. And well, the creation of that shock wave is the actuator, the special actuator that we are going to use. And I show you the result of the control. The idea is just to control, very easy control idea, control the speeds of the platoon downstream and upstream endpoints. And we can do that.
2 minutes left. Just
thank you.
Sorry, not to interrupt you.
Thank you very much. Well, I just mentioned the control problem faced in this paper, which has, well, actually, it's available online. It will appear next year. But anyway, in this paper, we have exactly used the model that I just mentioned, solving the problem of the minimization of the total fuel consumption for the vehicles involving a certain traffic system. We have some constraints to respect on the length of the platoon, on the velocity of the platoon, and on the difference between the upstream endpoint velocity and the velocity of the and back downstream, the back end of the platoon. We have a fixed bottleneck again. So this is the situation. We have used some model to describe, very classical model to describe the fuel consumption. We have reparameterized this model in terms of density. So at the end of the day, this is the problem that we have to solve, which is a fuel consumption optimization problem. And in this example, in which we have 200 cells, and we have 1 hour of simulation with the platoon realizing an occupancy rate of 0.6. So the platoon is reducing the capacity of the road in all the portions of the traffic system where it moves. We have this result. This was the open loop case, no control. So you see a very huge congestion due to the physical bottleneck, which tends to, of course, propagate in time and backward in space. And if you look at the effect of the platoon is to reduce a lot this congestion, creating some kind of, let me call, controlled congestion, which is definitely not so significant, not so heavy as the one. So this is a medium congestion traffic. So you look, we are here in the medium scale. But anyway, this is enough to solve the problem. This is done moving, changing the velocity of the front end and the back end, as said. And this is definitely better than what can be obtained by using a single moving bottleneck without controlling the length of the bottleneck. So using in practice the first PDE or DE model that I mentioned, not the one extended with the dynamics of the front end and the back end. And well, this is all for me. I hope to have touched all the point of my plan. It seems that I did. So I've introduced some new methods, starting from a review of the classical methods, and I've tried to show you how the use of curves in traffic systems seems very promising for controlling the system themselves. And this is all for me. Thank you very much for your attention. Thank you, of course, to my co-authors and collaborators.